I would like to start welcoming you all to the 27th webinar of the graduate program in physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave the microphone and the cameras turned off, except for the moment you're going to speak. Questions will be allowed in the end, unless otherwise requested by the speaker. The questions can be asked using the chat. Today, we have the honor to listen to Professor Anthony Z. Professor Z was born in China and was educated in São Paulo, Brazil, by American nuns of the Felician Order. He then went to Princeton University as an undergraduate and to Harvard University, where he obtained his PhD under the supervision of Professor Sidney Richard Colburn. Professor Z is an accomplished teacher who has authored or co-authored more than 200 scientific publications and several books. Among his books, I should point out his trilogy of graduate-level textbooks, namely Quantum Field Theory in a Nutshell, Einstein Gravity in a Nutshell, and Group Theory in a Nutshell for Physicists. He has written on particle physics, condensed matter physics, anomalies in physics, random matrix theory, superconductivity, the quantum Hall effect, and other topics in theoretical physics and evolutionary biology, as well as their various interrelations. He is also the author of several popular books about physics and Chinese culture. Over the years, his books have been translated into Chinese, both traditional and simplified, Japanese, Korean, German, Italian, Spanish, Polish, Czech, Russian, Turkish, and French, but sadly, up to now, given his connection to Brazil, not into Portuguese. We hope this scenario changes very soon. At present, Professor Anthony Z is a professor at the Clave Institute for Theoretical Physics and at the Physics Department of the University of California, Santa Barbara in the United States. But we are here today to listen to Professor Z, so I won't take your time any further with this introduction. Professor Z, thank you again very much for having accepted our invitation. The audience is yours.
Thank you very much, Professor Crispino. I'm very honored to be invited to give a talk in Belém, Brazil. I have a great deal of saudade for Brazil. When my father was alive, I used to go to São Paulo almost every year. But unfortunately, he had passed away. And now my opportunities for visiting Brazil is now much less. I was in Brazil several years ago, but the furthest north I got to was Bahia. So I've never been to Belém, I'm sorry to say. And I hope that one day I will get to see Pará and Amazonia. Okay, so today I'm happy to talk to you about quantum field theory and what I have understood of quantum field theory. Okay, so quantum field theory is arguably the greatest monument to the human intellect. And of course, now I hear all the humanities professors screaming, but in any case, it is the most accurately tested theory in physics. And it took a couple of millennia before we realized that the universe is pervaded with quantum fields, that we are surrounded by quantum fields. So for the students in the audience, they are naturally wondering, what is field theory and who needs quantum field theory? And needs is in quotation mark. Of course, these days, one doesn't even need to know quantum mechanics to be a professor of theoretical physics. Now, I must emphasize from the beginning that I'm not talking about experimental physicists for whom I have only admiration since they can do physics I cannot even dream of doing. But it's certainly possible to be a professor of theoretical physics without knowing even quantum mechanics. So, in fact, this question of who needs quantum field theory is addressed in the opening of my textbook on quantum field theory. And in fact, the first sentence of my book is, quantum field theory arose out of our need to describe the ephemeral nature of life. Ephemeral. The Chinese have a saying that life is just clouds and smoke passing in front of our eyes. But more seriously, we have quantum field theory, and we need quantum field theory when we confront simultaneously the two great physics innovations of the last century of the previous millennium, special relativity and quantum mechanics. So let me show you what I call the square of physics. So roughly speaking, the square of physics, does the pointer work? The pointer on my computer, I guess roughly. So on the horizontal axis, I have big and small. Now these dividing lines are just to guide the eye. There's of course no sharp division between big and small. And similarly on the vertical axis, it's slow and fast. So we are very large objects moving very, very slowly, lumbering around, and that's the domain of classical physics. So physics started in this area, and then Einstein showed us that we need to modify quantum classical physics when we consider objects that are moving very fast near the speed of light, but there's no need for quantum mechanics. Moving in this direction, the founders of quantum mechanics showed us that when, for example, when you have a slowly moving electron scattering off a proton, for example, in atomic physics, there is no need for special relativity. So it is in this peculiar confluence of special relativity and quantum mechanics that a new set of phenomena arises. So quantum field theory comes out of the marriage of quantum mechanics and special relativity. And because I'll explain, because of these things put together, particles can be born and particles can die. And that's why I said that quantum field theory is needed to describe the ephemeral nature of life. So after quantum field theory, physics has a new phenomenon that particles can be born and particles can die with some kind of life in between. So let me remind you, how does this come about? Let me remind you of the two gold-plated equations of physics. The gold-plated equations of quantum mechanics is the uncertainty principle of Heisenberg, that there's an uncertainty in energy which is inversely proportional to the uncertainty of time over the time period in which you do the measurement. So here's the advertising slogans for what this equation means. The slogan, the advertising slogan I like to call it, is that accounting errors could be tolerated for a short time. So the accountant could make a mistake, but then it has to be quickly corrected. Okay, so that's one of the key features of quantum mechanics. Now, the key feature of special relativity is that energy is equivalent to matter. So the gold-plated equation, as everyone knows, is E equal to mc squared, which says that accounting errors could be turned into stuff. So we need both quantum physics and special relativity for particles to pop out and pop into the vacuum. Okay, so when you have quantum mechanics, you would have accounting errors that could be tolerated for a short time. Over a very short time, we can have some fluctuation in energy. But without special relativity, that energy would just disappear. But with special relativity, the energy could be turned into stuff. So it could be turned into particles. And so particles could pop out and pop into the vacuum. Particles can be born and particles could die. Now, this could happen in two different ways. And this is a highly non-trivial statement because before 1964, before Hawking, people thought there was only one way in which this could happen. So it could happen if energy is available, for example, in an accelerator, or near a black hole horizon. That could also happen. So perhaps some bright young people in the audience could think of a third way. Don't say it's impossible, because before 1964, there was only one way that's possible. Now, in contrast, when you take a course on non-relativistic quantum mechanics, no matter how you shake and bake the Schrödinger equation, it's always the same particles. If you wrote down the Schrödinger equation with 7 electrons, then no matter what you do, there will always be 7 electrons, not one more and not one less. So let us talk about what a quantum field is. So first we start with classical field. So let us consider the example I like is to think of a mattress, and a mattress here, physicist mattress, it's just a bunch of mass points connected by springs, and so this thing could vibrate up and down. Far away, on distances scale much larger than the lattice spacing, that is the distance between these mass points. This would look like a continuous field, but on which it's when you can form wave packets of the normal modes of vibration, and these normal modes could propagate and move around. And if the springs is slightly anharmonic, if they're not completely harmonic, if it's harmonic, the wave packets will pass through each other. But the anharmonicity causes these wave packets to scatter and decay. So particle physicists realize that could be used to describe particles very early on. So particle physicists realized from the very early on that fields could be used to describe particles. So let's draw space and time, draw a space-time diagram. So imagine there's a source, which I denote by J1, and it could produce a particle, and the particle could propagate and be absorbed at a sink, which is called which I denote by J2. Now the next thing is then from particles to force, from field to particles, and how does a particle generate a force? Now when we study physics, the professors talked about force from the first day, but he could never explain before quantum field theory, there was no explanation where forces come from. Forces would only come, the professor can only describe what the forces are. But when you have particles, we know that the exchange particles can produce a force. And the analogy I used in my book is that the pi meson, like a marriage broker in the old days, which is rather a heavyweight lady whose inclination to travel is limited by her weight. And this cartoon is taken from my book, Fearful Symmetry. So I first thought about writing a textbook on quantum field theory, but I happened to be visiting the University of Texas, where Weinberg, who was supposed to be my professor, it's a long story, how I switched from Weinberg to Coleman. And his advice, this was in 1984, he said, you should write a popular book before writing a textbook. And he said many physicists who write textbooks don't know how to explain things at all. And writing a popular book to people who don't know any physics is the way to, is It's the best practice to learn how to explain things. So I wrote this transparency for the talk I gave a couple years ago. So here it says 34. I guess I have any greater than 34 years after German, Spanish, Chinese, Japanese, Korean translations. A French translation came out in 2018. So as Professor Crispino said, I'm hoping that there will be a Portuguese translation soon. So this is the French version of my book. And the Germans invited me to India, and this is Max Muller-Bavin. And I was actually paid by the United States government. And interestingly, when my book first came out, the newspaper in Calcutta ran such a headline, and this was extremely embarrassing because once they had a headline like this, some of the Indians thought that I was a religious leader, and I could start a religious cult. You know how in India it's people follow religious leaders and holy men everywhere. So the text of my talk in Mumbai was published in an illustrated by works on Indian art. So to continue the physics, how do we go from particle to force? Well, since the early days of physics, as I said, the notion of force has been among the most basic and the most mysterious. We don't know where it came from. So it's with great satisfaction that physicists finally understood that the origin of force is due to the quantum exchange of a particle. So given this understanding, in 1934, Yukawa decided that a marriage broker must be provided for the strong interaction. And so this is the time meson as we know it, and this is taken from my book and from the talk that I gave in India. So another rough analogy that particles could generate force is when if you think of two lumps on a mattress, and the two lumps are two external objects, and the particles generate an attraction between them because the attraction is due to the distortion of the field. Okay, so quantum field theory can explain where forces come from. And our understanding of the physical world by physicists at this point is that the physical world results from a web of interaction, some attractive and some repulsive. So offhand, this is extremely mysterious. Why are some forces attractive and some forces repulsive? Now, quantum field theory, one of the great triumphs of quantum field theory is that it's able to answer why. The sign, so it's plus or minus corresponding to attraction or repulsion between like objects. And here I emphasize between like objects, between the same kind of object. It depends, it just depends on whether the spin of the intermediating particles is odd or even. So ultimately, the sign could be traced to the difference between time and space. So many of you in the audience who have studied special relativity, you know about the Minkowski metric. In the Minkowski metric of space-time, between time and space, there's a relative minus sign. So it's this relative minus sign that propagates into determining whether the force is attractive or repulsive. And this, for this, we need quantum field theory. So when it spins zero, we have an attraction. And so this was Yukawa's original idea, that you have a pi meson that could bring protons and neutrons together. And this is the strong nuclear force. And for spin one, we have a repulsion. And this is electromagnetism. The photon causes a repulsion between like charges. So charges that are the same kind, they repel each other. And spin two, those are the three forces we know, generates an attraction, and that's gravity, which the graviton generates an attraction between the apple and Newton's head. Okay, so Given these three forces, this produces a lightning history of the universe. Very quickly, the universal gravitational attraction due to the spin 2 particle produces the instability that drives the formation of structure in the early universe. The dense regions becomes denser, right, because the matter attract each other. And this is a well-known phenomenon in every country around the world, which is that the rich becomes richer. So dense regions becomes denser, and is how structures form in the universe. Now, the free streaming photons and neutrinos, they impose taxation. Okay, so it's some kind of taxation because neutrinos and photons could carry energy away. Early on, the photons was both doing this job, but later on, the neutrinos were more efficient. And strangely speaking, this term free streaming has now gone into popular culture. Now, young children think that free streaming just means watching movies. Then the attraction between the protons. So we have the spin 2 particles generating a attraction, and the attraction between the protons due to the spin 0 particles then ignites the stars and eventually form the rich variety of nuclei, and the attraction between the positively charged nuclei and the negatively charged electrons due to the spin 1 particle produce the atoms. So the history of the universe comes from the interplay between these three forces. Now we come to the concept of field. The concept of field goes back to Faraday. And Faraday came from an extremely poor background, almost Dickensian, and without a proper education, he never had an actual education. The mathematics of the continental philosophers were beyond Faraday. And so he was compelled to invent his own pictorial language, and the language he invented was called field. He called it a field. Now, Faraday, when he refers to the continental philosophers, he meant the physicists in France and people that were writing down fancy mathematics like partial differential equations and so on, which he was not able to understand. Now here, talking about Faraday, in my book, I like to make a side remark about basic versus research. This is always a topic of controversy in every developed country. In the US, we are moving towards applied research enormously, and which may or may not be such a good thing ultimately. So in this argument, you can think back to the time of Faraday. If the Royal Navy wants faster communications, so obviously the argument was for breeding stronger pigeons who can fly faster and go longer distances. Instead, there were some physicists in the basement messing around with wires and frogs. Who would you support? And it's obviously any reasonable government would support stronger pigeons, right? So that turns out to be a myth. So Maxwell's theory of the electromagnetic field contains two hidden symmetries that will rock 20th century physics, namely relativity, special relativity, Lorentz invariance, and gauge invariance. Now, in hindsight, why was Maxwell not able to see these two hidden symmetries? It's because of the terrible notation of the 19th century physics. So when I teach electromagnetism, I always ask students why the magnetic field is called H. And the answer, almost no student ever knows that, can answer this question. But that's because Maxwell used terrible notation. He did not use vectors as we know it. So every quantity is written out. So the three components of the electric field was EF and G, EF, G, and so the magnetic field is obviously HIJ. So this is how we end up with electric field being E and magnetic field equal to H. So you could imagine, instead of 4 Maxwell's equations, the way we now think about it, he had something like 20-something equations. And so the symmetries were completely hidden. So is it conceivable that some young people now could also discover some hidden structure in the theory we have now? Because the situation is similar. Yang-Mills theory is written in a terrible notation. And it is a redundancy in the description. As you all know, a gauge theory means that there are a lot of degrees of freedom that are not physical. So this recent development of twistor, so-called Helicity amplitude formalism, is perhaps the first step in fixing this, I think. So I'm very happy and excited that Roger Penrose received the Nobel Prize for twistors, for the twistor prism. And I'm also happy to say that my book, Fearful Symmetry, Roger Penrose is the one who wrote the foreword for my book, introducing my book. So coming back into quantum development of quantum field theory, already in non-relativistic quantum mechanics, we have this very strange treatment, this formalism that we teach undergraduates here in the United States and also around the world, which is that the photon comes from a field, is treated as a field, electric field, but not the electron. The electron is treated as a particle. So one is a field and the other is a particle. So in American slang, this is called half-ass treatment. I'm sure in Brazilian Portuguese, there's even a more colorful term. So this led Jordan, Heisenberg, Dirac, and other people to say that the electron, must also be a field. Okay. So now everybody is a field. All particles are excitations in some field. Now Fermi then had a revolutionary idea when he wrote down the theory of his theory of weak interaction. He said that since the photon can be created, electron can also be created. And this led to tremendous fight. I was reading Heisenberg's memoir not ago, and Heisenberg said that when he and Fermi proposed these ideas, the younger generation, the older generation, almost kicked them out of physics. And this is completely crazy. The electron originated in the nucleus in decay. How could the electron be created? But now we believe some fields and they could be created. In particular, the graviton that's responsible for the gravitational field is also just a particle like any other. And this was emphasized by, especially Weinberg's textbook on gravity. So if you read textbooks on gravity, there are two opposing points of view. There's the geometric point of view that emphasizes curved space-time. But then there's this other point of view that emphasizes the graviton. But somehow, both of these are consistent with each other because somehow the graviton is also responsible for the space-time arena in which all fields work and play. In my popular book, I use the following analogy. It's like when you go into a very avant-garde theater in which they present a very modern play. And it's so avant-garde, you discover there's no stage. One of the actors is the stage. The other actors are doing their thing on top of this other actor. So somehow, this is the basic mystery of physics, right? Somehow graviton is it somehow different? How do you make this graviton quantum gravity? How do you explain the cosmological constant? And with gravity, the square of physics I showed you would have to be replaced by a cube of physics because now we have a third direction. So after Weinberg told me that I should not write a quantum field theory book, I should write some popular books first. So I 2 popular books in physics, and then I was ready to write my textbook on quantum field theory. And so my book on quantum field theory was published in 2003. And here I had an enormous fight with my editor at Princeton University Press. And the result of that is that he eventually left, after that fight, he left Princeton University Press. And I like to think that they fired him because of this fight. So I wanted to have this cover, and he wouldn't let me have this cover. So he said, how could you have a painting for a physics book? So this guy is just completely... so they replaced him with a young woman whom I have been working with for almost 20 years now, and I'm happy to say. So here you see the students trying to reach this green field. And after reaching quantum field theory, you have to climb this mountain. This mountain represents string theory, and we don't know what is on the other side. Perhaps string theory, perhaps that's not even the direction. Perhaps it should explore what happens over here. In 2010, the edition came out in which I added various new things like Penrose's twistor formalism, and also treatment of the effective theory of gravity. So, and then this field theory book was translated into Russian, and the Russian physicists point out that in Russian is logically inconsistent. And now it's translated into Japanese. But in Japan, they split the book into 2 volumes, and only the 1 has come out. And the publisher explained to me why it was split 2 volumes, because they said the Japanese, their hands are too small. They cannot hold your quantum field theory book. Your quantum field theory book is too thick. So this is a completely crazy argument, because I can hold my book perfectly well in my hand. So some of the features in my quantum field theory book, when I wrote it, I wanted to be different from the existing textbook on quantum field theory. So one of the things I did in one of the important development in the last 20, 30 years is the rise of field theory in condensed matter physics. And in an earlier generation, when I was a student, already there was use of Fireman diagrams in field theory, but this is only perturbative. So this is much more significant. It's the non-perturbative understanding of quantum field theory turns out to be relevant in condensed matter physics. And many of you know already the quantum Hall effect, the microscopic degrees of freedom, of course, electrons. But the long-distance physics is described by Chern-Simon gauge fields with fractionally charged excitations. And so you see the degrees of freedom are completely different. And this is one of the very interesting features of quantum field theory. The long-distance degrees of freedom could be different from the short-distance degree. And another example of something I treat is the surface growth and renormalization group. And finally, also replica symmetry and supertree. And also in the book, I think contrary to the textbooks that I had as a student, because gravity has become very important, the old textbooks, gravity is almost none. The other thing is try to be much formalism, and so I put in some jokes in Galileo. So I want to mention to you that quantum field theory, the fact that we're still studying quantum field theory, is not a guaranteed development, because it has had 2 near-death experiences. So the first one was in the late 1940s, because he was unable to produce Lorentz covariant result, and because there are lots of divergences. And this was overcome, these difficulties. And as you know, by young people. So young people meaning Feynman, Schwinger, Tomonaga, and so on. And interestingly, the old people like Niels Bohr and so on, Landau especially, was urging that quantum field theory be left behind, that we needed something beyond quantum field theory. And Landau even went so far that to say that quantum field theory should be buried in physics. So interestingly, the young people were the revolutionary conservatives. Okay, I think Feynman used this phrase that he was a very conservative, but a revolutionary conservative. Again, in the late 1960s, there was this S-matrix school because field theory was unable to deal with the strong interaction. But again, people overcome that with, as you know, with QCD. And my professor, Sidney Coleman, described the triumph of field theory as a victory parade that made the spectator gasp with awe and laugh with joy. So I also want to point out that quantum mechanics is in some sense a 0+1 dimensional field theory. It's quantum field theory with no space, but with one time. And string theory, as you know, can be formulated in terms of 1+1 dimensional field theory. So field theory is very general. Okay, so when we teach or learn quantum mechanics, the most common formalism is either the Schrödinger or the Heisenberg formalism, which is conceptually more profound and leading naturally to quantum field theory. And the Dirac-Feynman path integral or the Schrödinger functional integral formalism is more appropriate for quantum field theory. So in school, we always learn about the two-slit experiments when we study quantum mechanics. There's a source that emits electrons, and a screen with two slits, and then the detector on another screen. And the electrons has a certain probability amplitude for going through one slit, and another amplitude for going through the other. Supposed to add the two amplitudes, and then square to get the probability. Interestingly, probably in 100 years of quantum mechanics, students almost never ask, what if there are three holes? Well, you can ask what if there's three holes. The professor will just say, you just add the amplitudes for going through the three holes. You add the three amplitudes. And then the student could ask, what if you put in another screen with slits? And the professor gets a little bit impatient and said, well, you add, again, there's a probability amplitude for going through this slit, and then that slit before getting to the detector, and you add all these amplitudes. But here's the most zen of all, and I imagine a student like Feynman asking this, but of course he didn't. But in my book, The Most Zen of All, you add infinite number of screens, and then you drill infinite number of holes in each screen. So here are the infinite number. You see the screens are all here. There are infinite number of them, but there are infinite number of holes that have been drilled. And so you don't see them, well, because the screen have infinite number of holes in them. So then this is the idea of the Dirac-Feynman path integral. You add amplitudes over all possible paths now. So it's an integral over all paths. So here's an illustration from a book I'm writing. It's the path integral applied to life. Okay, so the big difference is, of course, we don't know when our life would end. So there are many choices. One of them is many physics students perhaps follow this path, which is study now and party later. You can always go to parties later on in life, and then you enjoy the tenure life, becoming a tenure professor. Or in school, you party and party and party, and then you flunk out, you fail the exam, and then you go to Wall Street and you make billions of dollars. Or you can marry a rich man or marry a rich woman, And then you can be so rich that you can fund a physics institute. But then eventually become an alcoholic and you get drunk. You became a total drunk and you die from drinking. Or instead of studying, you can go to the gym and lift weight and get a lot of muscles. You get a job as a bouncer in Las Vegas. And eventually they found your dead body in the gutter. Okay, so it's a path integral formalism tells you to sum over all these different paths. So quantum field theory, to simplify enormously, is really just one great big fancy sum, because you have to add up all the paths. And the fancy sum is, of course, what we call an integral. So an integral over some field, which you call phi, and phi is a function of x and t. And x could be chosen to be d-dimensional, and that's what I meant when I said when d is 0, it means it does not depend on x. And then there's an action s, which is functional of phi, and then you do this integral. And to understand this, so for students who want to know what quantum field theory, it really is just this integral, a very big fancy integral. Now, to help the students, we can imagine making it simpler and simpler. This arrow going down means becoming simpler. So one step down, we go down to quantum mechanics. Then we have a new name for phi. We can also call it the coordinate or position of the particle. But as I said, it's in 0 plus 1 dimensional field theory. So that means no x, no time. I'm sorry, no space. So just phi of t. And this we call q as the position of the particle. Phi of t is the position of the particle at time t. Okay? So you do this integral and you get quantum mechanics. We go even one step down. We go to what is called random matrix theory, which Professor Crispino mentioned in the introduction, in which phi does not even depend on time. But then, of course, it's trivial. It's just an ordinary integral in calculus, one more step down. But random matrix theory is the next step up, which was proposed by Eugene Wigner, which is to make phi into a matrix. Okay? So in some sense, 80 years of quantum field theory consists of finding methods or tricks to do this integral. So for example, lattice gauge theory is to replace this integral by a summation and use computers. So in some sense, it was going backwards from Newton and Leibniz. So what is the simplest method for doing an integral like this? Well, here's an example. Suppose I have an integral and s of phi is equal to this. Now we know that if there's no phi4 term, this is a Gaussian integral, which we know how to do. But what if we have a phi4 term? Then we cannot do this integral. It's impossible. Nobody knows how to do this integral with g phi4. Then here's the fabulous idea. The fabulous idea is that you expand this g phi4 in a Taylor series, in a series in G. And then you have phi to the 4n, and now these integrals could all be done. And then you have to keep track of all these integrals and add them all up. And so you draw little diagrams to keep track of the terms. So when I was a student, I remember I was really eager to learn about Feynman diagrams, which I heard so much about. So people are talking about Feynman diagrams, and everybody, all the professors, I said, could you explain Feynman diagrams to me, and so forth. But Feynman diagrams, if you don't know what they are, it's just based on this idea. You do the integral by expanding the part by making a Taylor series expansion, and then you draw little diagrams to keep track of the terms. Okay, and this is how I explain it in my textbook. If you need more detail, at least I speak for myself, can carry out this, but I certainly cannot to know how to solve every problem that has been solved, and cannot understand, can only understand what he created. But notice, also has a list of things to learn. Can you read this here? It says to learn. And interestingly, you see he crossed out what he has learned. And one of the things he crossed out was Kondo effect. He learned it. The quantum Hall effect, it was still on his blackboard. So several years later, when I visited Caltech, they let me use Fireman's office. I was very honored, but unfortunately, by that time, they have already cleaned the blackboard. They rubbed everything out. Now, Fireman, everybody worships Fireman, and there's not enough worship of Schwinger, and Schwinger, and I think this was very unjust, because Schwinger actually beat Fireman, as you probably know. After the war, they were both racing to calculate the anomalous magnetic moment of the electron. Anomalous means deviation from Dirac's value. And in 1948, Schwinger beat Fireman, and Fireman lost the race. And the answer, the expression for the magnetic moment is carved on his tombstone. So if you ever visit Cambridge in Massachusetts, you should go to the cemetery and to visit Schwinger's grave, and you would see this formula for the anomalous moment on his gravestone. The current value for the anomalous magnetic moment of the muon is given by this, and Schwinger got the 116. So imagine that now the agreement between theory and experiment is up to here. So I said in the beginning that theory in physics and get a rough idea. So to put the accuracy in rough pictorial perspective, consider him, even from other countries in South America. So I looked up the other day on Google Map, and I was surprised to see a Santa Barbara do Pará, but it's not the Santa Barbara I live in, but a different Santa Barbara, and it's about 48 kilometers away. Then I imagine those of you who have been in Belém have been to this place, so imagine driving there in 50 kilometers. Then the present uncertainty in quantum field theory between theory and experiment, the discrepancy is approximately 2 × 10⁻³ millimeter, which is, I don't know why which is the width of the human hair is about the same order as this. So just can you imagine if you drive that distance and you're off by 10⁻³ millimeter, and that's the incredible accuracy of quantum field theory. And students are always surprised when I tell them that quantum field theory has been tested to much higher accuracy than Newtonian physics. Okay, so this is from my field theory book and about Schwinger's triumph, and you have to calculate this Feynman diagram. Okay, so we only have to calculate, in fact, only one Feynman diagram, which is this one. Okay. Now, I mentioned Feynman diagrams because Schwinger was very upset. Of course, Schwinger did not use Feynman diagrams. And Schwinger said, Feynman brought quantum field theory to the masses. because now all you have to do is that you have to learn Feynman diagrams, how to draw Feynman diagrams and calculate, and you can claim to know quantum field theory. So one of my colleagues in Santa Barbara used to refer to those people who can only calculate Feynman diagrams and think that they understand field theory as professors of Feynman diagrams. But anyway, the story is, of course, that Schwinger would not allow Feynman diagrams at Harvard. So when I was a student and I took a quantum field theory course from Schwinger for 4 different years, so 4 times in 4 different subsequent years, and Schwinger never mentioned Feynman diagram, not even once. He never drew a diagram. And some of you may have heard of Martin, especially in condensed matter. He's a very distinguished condensed matter physicist who was a student of Schwinger's. He was a generation older than I am. He was a professor when I was a student, and later he became the chair of the Harvard Physics Department. In 1979, he wrote an article about how Schwinger would not allow Feynman diagrams. So what students did is they go hide somewhere. Lyman is the name of the building at Harvard, in the dark recesses of the sub-basement. The basement is not enough. They were afraid not just to go down to the basement, but to go down to the sub-basement, below the basement, where the theory students could now draw a diagram where the ritual taboo on pagan pictures could be safely ignored. So when I was a student, Schwinger's student also told me the same thing. They went home and calculated using Feynman diagram, and then they translate everything back into Schwinger's formalism. And they would never confess that they actually got the result by using Feynman diagram. So here's a picture of Schwinger and Feynman at the Nobel ceremonies. And the 2 people could not be more alike. And this is what is so amazing. And recently, Stanley Desser, who was a student of Schwinger's, wrote a very interesting article about these 2 great physicists. And that they came out the same cultural background. They both came out of middle-class Jewish families in New York City. But yet their personality is totally different. Feynman is like a Las Vegas showman, and Schwinger is very, very shy, but a very, very nice person, very nice to students. Feynman, on the other hand, could be extremely nasty to students. And you can see at the Nobel ceremonies, Feynman is like talking away in his usual way. And Schwinger, you see they wore white gloves, I guess, to shake hands with the king. And Feynman's already taken off his gloves. And you can just see the body language of Julian Schwinger. It's like he tries to get away from Feynman. I don't want to be near you. He wants to get away. So here are some landmarks of quantum field theory in the 20th century. So first, Heisenberg opened up internal space by introducing isospin. And then Hermann Weyl finally recognized gauge symmetry in quantum field theory. And then Yang-Mills, as you all know, generalized the gauge symmetry, combined the gauge symmetry with Heisenberg's isospin to write down non-abelian gauge theories. And so recently I'm writing a popular book on quantum field theory because my editor at Princeton University Press, I'm sorry, I'm getting ahead of myself. So my editor Ingrid at Princeton University Press kept telling me that since I've written a book on quantum field theory, a lot of undergraduates wants to learn quantum field theory. So at her urging, I wrote a simple introduction to some topics in quantum field theory for undergraduates in this book called Fly-by-Night Physics, which came out in October 2020, just a few months ago. So I talked about Feynman diagrams, the influence of Feynman diagrams on quantum field theory for many years. And in fact, this influence persisted to the time when I was a graduate student. I was even told by one professor that quantum field theory is equal to the sum of Feynman diagrams. I think that was the attitude that was very common at that time, that quantum field theory just equal to Feynman diagrams. So one of the historic events occurred in the mid-1970s, and I refer to that in my book as breaking the shackles of Feynman diagrams. So breaking away from Feynman diagrams, and again, it was two young people, Hooft and Polyakov, independently. They discovered effects in quantum field theory, such as magnetic monopoles. Their properties go like e to the minus 1 over g squared, which, as you can see, is not analytic in g squared. So this can never be seen in Feynman diagrams. You can expand in g squared, and you never see this term. So since then, there have been a lot of non-perturbative phenomena discovered in quantum field theory, duality, topology, and so on. So finally, and I'm getting to the last part of my talk, and I know that some of you are worried about time, and so am I. So I'd like to ask, what is the purpose of studying physics? I often ask the students in the United States. And the correct answer is the purpose of physics is to understand nature. So some students answer the purpose of physics is to make money. And okay, that's a possible answer, but that's not the correct answer. I have one student, one graduate student, who after studying, getting his PhD in physics, went off to Wall Street and made a lot of money. And that is fine, quite perfectly good. I hope he funds some physics institute. But for our talk here, the purpose of physics is to understand nature. Now, then I like to introduce a criterion and talk about the intellectual completeness of different areas of physics. So for example, there's the Pauli exclusion principle and the spin statistics connection. Integer spin, we know, are bosons. Half integer spin is equal to fermions. There's a book by Duck and Sudarshan on talking about the Pauli exclusion principle, the origin, the history, and so on. And I highly recommend to you this book. Duck is not American duck, but it is the German. He's a German, and it's actually Duke with the umlaut, in which they say there is no one fact in the physical world which has a greater impact on the things, on the way things are, than the Pauli exclusion principle and the spin statistics connection. And this is true when you think about atoms. Atoms would be much, much smaller if there was no Pauli exclusion principle. To neutron stars, to lasers, because the coherence between bosons, between photons, much of condensed matter physics, band structure, superconductivity, etc., etc. So in some sense, Duck and Sudarshan argue that this is one of the most important facts in physics. But in non-relativistic quantum mechanics, it's just a fact, it's just a rule. So to the students in the audience, if you are taking a course on quantum mechanics, you could come from, and you explain, derive Pauli exclusion principle for me, and the professor cannot, okay? Because you can only derive it in quantum field theory. So in this sense, quantum field theory is intellectually more complete than quantum mechanics. There are things in quantum mechanics. Let me ask you another question. You could ask, when you're taking a quantum mechanics course, the students should ask the professor, how do you know that all the electrons are identical? Well, how do you know that all the electrons in the universe, they could have been made in a factory somewhere, okay? So we need quantum field theory to explain this fact. There's probably almost no fact more basic than this. All the electrons are identical. They have the same mass, the same magnetic moment. So quantum field theory gave us an elegantly simple explanation. It is so elegantly simple that it absolutely must be correct. And it is so simple, it could be explained to a child, because all the electrons are just excitations in the electron field. They're all excitations in the same charge, exactly equal in magnitude to the proton charge. Well, quantum electrodynamics cannot explain this. Feynman could not explain this, right? In QED, you can put in any charge for the particles you like. So in this sense, quantum dynamics is less intellectually complete than grand unified theory, which I don't have time to talk about. But in grand unified, equal and opposite. Why is space-time 3+1 dimensional? Well, quantum field theory can be written in any space-time dimension, unfortunately. And I say unfortunately, and so it is less complete than string theory. In fact, one of the remarkable things about quantum field theory is that it is very accommodating. You can write down quantum field theory to violate CP violation. You can write down quantum field theory that violates parity. You can write down quantum field theory to violate a lot of different things. So it's intellectually less complete than string theory. It can be written down in any dimension. But of course, strictly speaking, string theory also cannot explain why it's 3+1 dimensional. String theory can explain why space-time is 9+1 dimensional, but not 3+1. So we are waiting for some young person to come and explain to us why space-time is 3+1 dimensional. So let me close by mentioning one of the deepest mystery in physics is that the dynamical evolution in the quantum world is given by this unitary generator, e to the minus iht over h bar. And the Boltzmann factor in statistical mechanics, e to the minus beta h. And so imaginary time and inverse temperature are related. So is this just a coincidence or whether it's deeper? Well, we don't know. So in any case, this can be applied. This coincidence, we can take advantage of it, we can exploit it. For example, we can derive the Hawking nature of a black hole by using this correspondence. Okay, so the partition function then can be represented as a Euclidean field theory in contrast to Minkowskian field theory, because it's like imaginary time. So time now has the same signature as space. So many other problems in physics, now many of the methods can now be used. So, talking about two great marriages, the great marriage of the 20th century was combining quantum physics and special relativity, and they produced quantum field theory. In the late 20th century and the early 21st century, people were trying to combine quantum physics with general relativity. So Einstein had two daughters, special relativity and general relativity. Special relativity has been married to quantum physics, but not general relativity. So we don't know what it would produce. Some people think it's string theory, but we don't know. So this ends my talk, and thank you very much. Dan, thank you.
So we thank you, Professor Z, for your excellent talk. So first of all, I ask everybody, as it's the tradition here, to turn on their microphones for a huge round of applause to acknowledge this excellent talk. I ask everybody to turn off their microphones again. And so we have already some questions that we will make in the order of the registration. But before that, while people write down other questions, let me take this opportunity to give you an overview of the audience that you had. So I'm very happy to tell you that you have had one of the biggest audiences of the webinars that we have organized here, around 200 people joining together Google Meets and YouTube. And from almost 20 different, almost all Brazilian states and the Brazilian capital. So from all the 5 regions of Brazil. So I will mention the states only: Amapá, Pará, which is where we are, Amazonas, Alagoas, Bahia, Ceará, Maranhão, Paraíba, Pernambuco, Rio Grande do Norte, Distrito Federal, Goiânia, Rio de Janeiro, São Paulo, Minas Gerais, Espírito Santo, Santa Catarina, Paraná e Rio Grande do Sul. So obviously, undergrad, graduate students, postdocs, teachers and professors from our own graduate program, our teachers and professors like Professors Leon, Clautal, Macedo, Alves, Castilheiras, Alves, not only from the capital, Belém, but from all around the surroundings of Belém in the state of Pará. There's already a huge state, cities like Abaetetuba, Bragança, Castanhal, Salinópolis. And you have had a lot of teachers and professors from several universities and institutes from different states, and even from different areas of knowledge. And I will mention some of them since it has been recorded, like Adilson Silva from USP, Antônio Soares, Carlos Almeida from Ceará, Cecília Quirente from São Paulo, Edson Moreira from Unifei, Enzo Granato, Jorge Matas, Giorgio Torrieri, Júlio Fabres, Marco Casals, Marcelo Gomes, Marcelo Nai, Marcos Maia, Múcio Continentino, Nelson Studer, Nivaldo Lemos, Paulo Silva, Rodolfo Casana, Satiscuma, Silvio Salinas. So I'm sorry, some of these have been even the professors of the students under quantum field theory. So, I mean, it's very nice to have them here in the audience. And I should also mention that we have people attending us from abroad, like Alberto Sá, that is attending from Portugal, although he's from Unicamp. Alexander Kamenchik, that I believe is attending from Italy. Jaime Redondo from Madrid in Spain. Humberto Huerta from Mexico. Elias Metakas from Sweden. Servio Merchancano from Colombia. Pedro Baca from Mexico. So South America, Latin America, even Europe. So I'm really happy. I mean that
I'm
so
very happy about this. Thank you all for listening. Thank you,
Professor Z. So the first question registered here comes from Satish Kumar VH. So Satish, do you want to make the question yourself?
Yes. Thank you, Luis. Thank you, Dr. Z, for the nice talk. By the way, look here. I have your book right with me. I have thoroughly enjoyed your book, Fearful Symmetry. It has beautiful pictures, reminds me of George Gamo's book. And I think even kids love your book because it's the only physics book with Humpty Dumpty.
Yes.
With that said, okay, I have 2 questions. The first question is, you mentioned about spinor helicity formalism and twistor theory, right? So I know there exist methods for calculating the scattering amplitudes, but are they related? That's my first question. The second question is, you also mentioned that S-matrix theory failed to explain the strong interaction. But is it good for other interactions like electroweak and QED? Can we do QED in S-matrix formalism? And what's the fundamental difference, perhaps philosophical, in the formulation? Difference between S-matrix theory and quantum field theory. I have a third question. Maybe I'll come to this only if the time permits at the end. Thank you.
Well, thank you for your questions. I think, and especially for mentioning Humpty Dumpty. So let me just answer the second question first. Well, as you know, S-matrix theory was used because they didn't know how to deal with the strong interaction. But nobody ever suggested that we need S-matrix theory for electromagnetism and for the weak interaction. And now we know that we don't even need S-matrix theory for the strong interaction. We now have QCD, which is a perfectly fine quantum field theory. It may be in the future that we would encounter some phenomenon that somehow cannot be explained by quantum field theory. That's completely possible. But at the moment, I don't see any need for simply S-matrix theory. Could you remind me of the second question, the first question again?
It's the relationship between the Spinor-Helicity formalism and the twistor theory.
Oh,
I thought they're two separate things, but are they related?
They are the same. And you know, the twistor formalism has a long, difficult history. And because, as you all know, Roger Penrose is a very imaginative guy. And he throws in a lot of different things into his books and so on and so forth that many people don't believe in. And so, for example, he's claiming there's some evidence of a universe before the Big Bang and so on and so forth. So, so I was told, I myself have not been working on Helicity amplitude. So I asked one of the Helicity amplitude people why they invented a different name. And they said because they, you know, for many years, twistor has a sort of a bad name to it. So that, but Helicity amplitude and twistors are really the same. They're really related. By the way, I've given some lectures in Sao Paulo about twistor formalism and Helicity amplitudes about 10 years ago. Okay, so they are the same. Thank you.
Thank you. I'll look into those things. Thank you very much.
Okay, thank you, Satish, for your question. Thank you, Professor Z, for your answer. So the next question comes from Gabriel Luz from Rio Grande do Norte, Natal. Gabriel, do you want to make the question yourself?
Yes, thank you. First of all, the three books that you have that ends with in a nutshell, they're brilliant. So I was wondering if you are going to make more books with this title, possibly a string theory book.
No, in fact, there's a, thank you for asking that. In fact, there's a very interesting history about this. I proposed the title Quantum Field Theory in a nutshell. And the editor I had, I mentioned it's this editor, and I had a big fight about my book. And so he objected to the term in a nutshell. He did not want that, and he said that's that cannot be. And then he objected to this title. But I did not tell you, he objected to this painting. But I also did, I did not even tell you what his objection, his other objection was. He spent a lot of time on this Q. And so we had big arguments about this Q. And then eventually, as I said, he left Princeton University Press. I like to think he was fired. And you know, the other thing that he objected to, which was incredible, he said, why the Fireman diagrams are black lines on white paper. So in the book, the Fireman diagrams, of course, drawn with black lines on white paper. And he said, you physicists always write things on a blackboard. So it should be white with white chalk. So it should be white lines on the black background. And so I said, I absolutely refused, because then the Fireman diagrams in the book, they would all look like black smudges. You turn the pages, you see all this black stuff. And so I had so many arguments with this guy. So I like to think that because of our big fights, he left. And so he objected to this in a nutshell. But the woman who took over this job. Ingrid Nerlich, whom I've now worked with, as I said, for almost 20 years. She liked this in a nutshell so much that she decided to start a whole series of books on something in a nutshell, something in a nutshell. So there's now, I don't know, maybe 15 books called published by Princeton, and there was a book called String Theory in a Nutshell. But some of the books are good, and some of them are not so good. The Astrophysics in a Nutshell is very good. I enjoy reading it. But there's a terrible Quantum Mechanics in a Nutshell. It's written by some, well, anyway, I shouldn't say this in public. Okay. So I don't have any plans for writing more books in a nutshell series. My most recent book is Fly-by-Night Physics. But perhaps I could mention that Ingrid, the editor, wants me to write a book on quantum field theory for the general public, for a popular book on quantum field theory. So this talk that I just gave is based on my textbook, Quantum Field Theory, but now there will be a popular book based on this talk. So this talk will become a popular book eventually.
Okay, thank you very much.
Thank you, Gabriel, for your question. Thank you, Professor Z, for your answer. So the next question comes from Jorge Matas. Jorge Matas is speaking from São Paulo. Let me take this opportunity to mention that he has been my PhD supervisor, doctoral supervisor. So he's kind of my academic father. But due to the difference in age, it's not so far. So I'm more comfortable with saying he's my older brother with many very important advices and teaching that he gave me. Matas, do you want to make the question yourself, or do you want me to read it?
Yeah, I can speak. Thank you, Luis. That was a long time ago. So anyway, so Tony, thank you very much for your very nice tour through quantum field theory. And I would like, at some point of your talk, you very nicely said that the purpose of physics is to understand nature. And I agree completely about that. And you also described in this nice cover of your book, these little mountains as representing string theory. So I would like to ask your opinion about the following. After 40 years of string theory with no confirmed prediction, so I would like to know your opinion about what must happen for people to stop pursuing stop pursuing string theory.
Well, I am not the one to ask this question because I don't work on string theory. And unfortunately, we live in democratic countries, so nobody has the power to stop people from doing string theory. So, as you know, Landau actually did try to stop people from doing quantum field theory, and he succeeded to a large extent. Okay, so
no, I mean string theory, right? I'm talking about string theory, not quantum field theory.
I know, but who has the power to stop people from doing string theory?
Okay.
And Tadeusz Popov happily ignored Landau and published anyway.
Yes.
Okay, so thank you, George, very much for your question. Thank you, Professor.
Can I maybe add a remark?
Yes, please.
I would also like people to remember, since you mentioned that you're in Sao Paulo, to people to remember George Sveka, who died unfortunately very young. When I was a student, I would come home from to visit my parents from Princeton in the summer, and I would go to the university, and I would ask George Sveka questions about physics, and he's the one who taught me spontaneous symmetry breaking and the Goldstone theorem and all that. So it was terrible because at that time Sveka was considered the future of theoretical physics in Brazil, and the fact that he died so young was really tragic news. Okay.
Okay, thank you. It's very good that you mentioned Vieca. Vieca is a reference for all of us Brazilians. Even we have a school, a traditional school named after him. So let's pass to the next question. So it comes from Gabriel Young from Florianópolis, Santa Catarina. He's attending from YouTube, so I have to read it. Do you believe that an eventual unification of quantum mechanics and gravitation should regard gravity as created by a particle? The equivalence principle would be ruled out in such a theory?
I don't understand the question, because in the present formulation of gravity, the gravitational field is described by a graviton, and I don't see how that would rule out the equivalence principle. Allow me to add one remark, since Louis mentioned that there's a school in memory of Sueca. I have actually lectured in that school many years ago once. Yeah. Okay.
Okay, so thank you very much, Professor. Let's then move to the next question. It comes from Igor Moll, who's doing his master's in Rio de Janeiro. So Igor, do you want to make the question yourself?
Hi, I would like to ask the question, and I am very sorry by accent anyway. So first, thank you for your great book, which I am using right now in a class. It's very funny, it's very enjoyable, and maybe someday you can give me an autograph. And to Gabriel, I think there is a string theory in a nutshell by Elias, which is not so bad. In any case, following the logic which he gave to us in the last part of the lecture, science general relativity is a contradiction of string theory. Would you not say that superstring theory is more complete than any physical theory known so far? And if I could make another question, what's your standing in the following matter? Do you believe that gauge symmetries are just redundancies, or that gauge symmetries is fundamental, considered as a connection in a fiber bundle in which the curvature is the field strength, like in general relativity? Thank you.
Well, thank you. I don't think I completely understood the question, but I heard something about fiber bundles and curved space, time, and so on. So in the United States, at least when I was a student, they were sort of split into two groups, but the majority belonged to something that maybe I refer to as the Fireman shut up and calculate school. So this was very anti-mathematics, and I was never at Caltech, and I met Fireman a few times, but I never studied physics as a student with him. But some of my professors at Princeton were very much influenced by Fireman. And so in particular, I remember one of my professors telling me that if you, to do good physics, the most advanced mathematics you need is Cauchy contour integration. And many years later, when I was working on the quantum Hall effect, I went to Texas. That was, in fact, the same occasion that I mentioned in my talk, when Weinberg and I started talking about writing a quantum field theory book. And I gave a talk about Chern-Simons theory and the quantum Hall effect. And after the talk, Weinberg took me aside And he said to me, he said, young man, you know, if you want to do physics, you should stay away from mathematical stuff, from this mathematical stuff like Chern-Simons theory. So I tell this story as a joke because that at that time, Weinberg would consider Chern-Simons as unbelievably mathematical. But now, imagine the mathematics that people are using in string theory and so on and so forth. And there's a lot of people that like to use all kinds of mathematical terms, but I'm not one of them. So I'm sorry, I can't, that's all I can say about the question. Thank you.
Okay, thank you, Igor, for your question. Thank you, Professor Z, for your answer. So we have some other questions, Professor. So one question came from YouTube, from Anna Blasco. She has written, what is, in your view, of the feasibility of building or translating quantum field theory considering the Bohmian interpretation of quantum mechanics? David Bohm.
Again, I have to plead ignorance. I don't know enough about Bohm's formulation, so, but I understand that he was, I can tell a little story instead, perhaps. Many years ago, you know that late in life, Bohm had its interest shifted to a lot of philosophical and perhaps even religious matters, and his interpretation of quantum mechanics and so on and so forth. So he was invited to give a lecture at the University of California in Santa Barbara. But he was not invited by the physics department to give this lecture, but he was invited by maybe people in philosophy and religion, and so on and so forth. And one of my colleagues in physics introduced him. I had dinner. I was honored to have dinner with Bohm, and whom I consider to be a great physicist. I had dinner with him and another physicist, an older physicist who introduced Bohm. But I thought the introduction was shameful, or just shameful for such a great physicist like Bohm. And the introduction was something like, the physics department did not invite him, and anything he says is not physics. And I thought it was terrible. Anyway, so that's my answer. Not really an answer, but just a story.
Okay, thank you, Professor. As we all know, David Bohm spent some time in São Paulo, right? And so let's move to the next question. So Edson Moreira from Itajubá, do you want to turn on your microphone and make the question yourself? Edson, please.
You can do it for me, Crispin, please.
Yeah, so in your opinion, what is the role of black holes in quantum field theory?
I think it's extremely, of course, everybody thinks it's extremely interesting, and I think it's extremely interesting. And there's a lot of, well, what more can I say? And many people think it holds the key to understanding quantum gravity. Many of my colleagues, especially Professor Poczynski, his office was next door to my office for many years, and tragically he passed away, even though he was 9 years younger than I was at the time. And he always told me that black holes were, that this Hawking's discovery was one of the most important in this second half of the 20th century. But I'm not sure what you want me to say. There's not anything I can say, really. People have been studying black holes and very intensely. I mean, what? Yeah.
Okay. Okay, Ed, so maybe if you want to complement, please go ahead. Otherwise, I'll thank Professor Z for his comments. And Satish from Unirio has another question. So Satish, would you like to make it, please?
Thank you, Luis. Dr. Z, I'm asking this question because you mentioned the book of Duck and Sudarshan, right? As you said, there is no non-relativistic proof of the spin statistics theorem, right? Which is Pauli exclusion principle,
Right.
which is very much at the heart of quantum mechanics. So does it mean that quantum mechanics already anticipates special relativity, although it's not written in a Lorentz covariant way?
I don't see how. I thought that when you started asking this question, I thought maybe you were one of the people. There are people that claim drive the spin statistics connection in non-relativistic quantum mechanics, but I don't think those proofs are generally accepted, and I don't understand those proofs at all, because obviously I think for people in the audience who know quantum field theory, you can write down a non-relativistic field theory without that violates the spin statistics theorem. So I'm not exactly sure how those proofs work. I thought you were going to ask that, but again, I don't know.
No, I haven't published any work on that.
Yeah. Good.
Okay, so thank you,
thank you,
Satish, once again for your additional question. Thank you, Professor Z, for your answers. And at this moment, we are coming to the end of this very nice moment spent together with Professor Z with this excellent talk. And I would like to everybody to turn on their microphones for a final round of applause in recognition and acknowledgement to this excellent talk.